All right, so for this problem, we're going to do a nodal analysis by inspection problem. Um, isn't too bad to do. It's a little different than we do our normal nodal analysis. Inspection lets us go a little bit faster, though, in some regards. So let's look. All right, so here we have a simple little problem. We have two current sources, a 10 amp one and a 5 amp one, and we have three resistors, a 2, a 4, and a 6. So first thing we're going to do, like any other problem, ref node. So we're going to make our ref node right here. Cool. Second thing we're going to do, assign voltages to nodes. So we got what nodes? We got this one and we got that one. So let's do V1 and V2. Cool. And that looks good to me. 3. Now this is the different one. Assign conductive / conductance. All right. So remember from chapter 1 and 2, actually, we had that conductance is actually 1 over the resistance. So we're going to do G equals 1 over R as our equation. Conductance equals 1 over resistance. So for this resistor, we're going to get the G equals 0.5, 1/2, because it's 1 over 2. For this one, we're going to get 0.25, because it's going to be 1 over 4. And for this one, we're going to get 1 divided by 6, which is 1.66. We can just put that as 1 over 6 equals G. So we're just going to circle that out, circle that out. You know what? I'm going to even highlight that to make it clear for you guys. Let's take yellow. Assign conductances. That's going to be yellow. That's our conductance. That's our conductance. That's our conductance. So we've got that part down. Now for build conductance matrix. So this is different than we've had before, but you've seen this probably in mechanics of materials. It's a similar take. We make our conductive matrix. Conductive matrix. And our conductive matrix is going to be G11, G22, and then the way I remember it is 1, 2, and then 2, 1. So G12, G21. So 1, 1, 2, 2, 1, 1, 2, 2. Cool. That is our conductive matrix. So now we've got to plug these things in. So how are we going to do that? Well, we're going to look at G11. G11 equals everything that's connected to voltage 1, V1, equals connected to V1. And I'm just making this, I mean, you can pick which one, V1, V2, but I'm going to do it this way, V1. Everything connected to V1. And for this, we're going to have that equals 1/4. So V1, we have a 4, 1/4 for the 0.25. Plus, we have V1 1/2, right? So 1/2. Anything else connected resistor-wise? No. So that's going to equal, what is that? 1/4, 1/2. So that's 3/4. 2 over 4 plus 1 over 4, 3 over 4. Cool. So that one's set. We're going to box that up. Cool. That looks good to me. All right. So now we're going to do, for the next one, G22. G22 equals connected to V2. And connected to V2, we've got two different resistors. We've got a 4 and a 6. And so here's what we're going to do. We're going to do 1 over 4 plus 1 over 6, and that's going to equal, what's the bottom piece? If we multiply this one by 3 and 2, 12. Okay, so it's going to be 12 on the bottom. Multiply this by 3, 2, 5, 12, I think. Yes, we're good. 5, 12. All right, so that's our G22. And now we've got our G12 equals G21. Now, why does 1, 2 equal 2, 1? Because what's connected between the two, between these two, is the same as connected between these two. It doesn't matter. It's going to be the same. They're identical. So that is connected equals connected between V1 and V2. Okay? And that's going to equal, well, there's only one that's connected between there, and we're going to put that in as minus 1/4. Okay, and that's going to be here. And we've got to make this negative to make this work for our conductive. So that's negative there. All right, so now we have this part done. So now we're going to make our conductive matrix and fill these into here, and then we're going to solve. So we've got G11, so let's just make our matrix up again. We got our matrix up. G11 equals 3/4, right? G22 equals 5/12. This equals minus 1/4, and this, as we plug into minus 1/4. Cool. That's the first part. And now we remember that our times V1 times V2, I did those. This is V2, 2, 2, 2, 2. Okay, that's fine. And that's going to equal, now we need to do the entrance minus the leave. So enter minus leave is the way I think of it. And so this is going to be another matrix here. And for this one, we're going to look at V1. So in V1, we have 5 amps in, and we have nothing written coming out. So we're going to do 5 for this one. Let's just check V1. You have 5 in, so that's 5 minus 0, so that's 5. And then for V2, we've got what? We've got a 10 coming in, and we've got a 5 coming out, and that's unwritten. So this is 10 minus 5, so that's 5 and 5. So we can take A to the minus 1 of B and get 13.3 and 10 coming out of that. And that is going to be equal to our V1, and that's going to be equal to our V2. Okay? So these aren't too bad to do. It's just a little different doing it with this matrix here. And we can go through a couple more of these. They're a little faster sometimes to do than some of the other analysis. But anything else for this? Let's fill it up here. So we didn't write all the steps. So once we built our conductive matrix, we have to find values. And that's what we did down here. Anything connected to V1, anything connected to V2, and then G1, G2, so the difference between the two, we make that negative there. All right, so that's the first bit. And then 4, 5, 6. What do we do after that? We solve the matrix equations down here. Solve matrix equations. And then 1, 2, 3, 4, 5, 6. Let's go to 7 here. Then we can also solve the node voltage equations. Cool. And I think that's all we've got for this one. That'll give us our V1 and our V2 with relative to that point. So, hope that helps. Let's do another one.